Kia ora koutou. This is a lovely question from the 2009 Scholarship Calculus exam, and it's one that somehow, I've just never seen it before, and I really like it. So it's a little conics question where we have to find a locus. We've got an ellipse, and the ellipse is drawn for us here. The ellipse is in, standard form, x squared over a squared plus y squared over b squared equals 1, so it's centered at the origin. And then we've got a point Q, which lies at the intersection of two perpendicular tangents to the ellipse. So here's point Q here, here's the first point on the ellipse, and here's the second point on the ellipse. And what we're asked to do is to show that if we move around here, and then the other point will move as well, that the intersection of the two perpendicular tangents is going to trace out a circle. And they've very nicely given me this equation here. I'll make it a bit bigger, which is that y equals mx plus or minus the square root of a squared m squared plus b squared. Now, the first time I saw this, I was kind of going, why on earth would I want to have this? But it's really useful. So this video is going to be quite slow. I'm going to start with a little example of an ellipse where we've got some numbers. So suppose that we've got x squared over 25 plus y squared over 9 is equal to 1. And we can draw that really quickly. Let's just put some axes in over here. Can I get the button? There we are. Yep. Right, so you should be pretty used to working with the a squared and the b squared. We can see that if x is 5 or negative 5, then this term here is going to be 0. So that's your reminder that that's my major axis. And here I've got 3 here and negative 3 here. Again, if this term here is 1, then this one's going to be 0. So we can trace out this. Okay, now suppose that I said, find me the tangent at this point here, right? So suppose we had x is negative 4, we'd figure out the y value, and off we'd go to get our tangent. And to do that, we would do our usual implicit, so we go, 2x over 25 plus 2y over 9, dy by dx equals 0, blah, blah, blah. And we do what we do with all other problems, right? So doing it that way, to get the tangent, we'd get m, and then we'd go y minus y1 equals m times x minus x1. I haven't prepared this ahead of time, so it's whatever that value there is what's going to go in here and here, right? And we do that lots and lots of times, and that's kind of, I guess that's probably achieved or merit conics for level 3. But what this formula here is giving us is something a bit different. It's saying that if for some reason we want to figure out the tangent line with a particular gradient, we can go straight to that by using this version of the line. So suppose I said, tell me the equation of the tangent with a gradient of 3 to that ellipse. So you can see from looking that that's going to be, a pretty steep line. So let's pop it in here in the yellow. And there's going to be another one over here. So when I taught this problem at our Saturday class yesterday, a couple of people said, what's the deal with the plus or minus? And that's what's going on with the plus or minus, right? We've got two straight lines with the same gradient, but with different y-intercepts. So this one here is going to be the one with the plus square root thing, and this one here is going to be the one with the minus square root thing. You don't really need any of that for this question, but as usual, the more confident and comfortable you are with the general form shown, the less you're going to freak out about what seems like maybe quite a hard question. So what we've got here, going back to the problem, is we've got an ellipse. It's got the basic form, so it's an ellipse centered at the origin, and we're going to be tracing out these points as we move around. So I put that into GeoGebra. Now, I couldn't figure out a way to have the tangents automatically tracing out and being tangent to the ellipse. So instead, I've just screenshotted a few cases, right? So this is the one like the one in the diagram. That's almost exactly a right angle. So that's our first point. And then I moved point A and B around a bit. So you can see that that point is moving out to about there. So I could have done some coordinates for these, right? But you can see that it's heading up to here. And then the third one I did was this one down here, and you get another point out here just out to the side. And what we have to show is that if we trace out all of those points, I'm going to do a bad drawing now. Let's see how it goes. We have to show that we're going to get a circle that does not look like a circle, right? But intuitively, and this is helpful for the problem, we can see that because the ellipse is an easy ellipse centered at the origin, the circle also is going to be centered at the origin. So that tells me that what I'm trying to get to in this problem is somehow to end up with the locus having this form here. X squared, or maybe, yeah, let's go back. If it's centered at the origin, it's going to be x squared plus y squared is equal to k squared. All right, so what have we got to work with? Well, we know the equation of this tangent line. We've just been given that here. So let's start by writing that out. And I'm just going to work with, I'll leave the plus and minus in, even though I think it might confuse my brain. That's tangent 1. Notice that we didn't have to differentiate to get that. We just plonk it in because we're given that information. Now, this other line here is perpendicular to it, and it's coming from the same ellipse. And we know that perpendicular gradients have to multiply to give me -1. So tangent line 2 is going to come from this equation, but we're going to substitute in -1 over m for the gradient. Okay, so m is the gradient of that first line, and -1 over m is the gradient of the second one. And that means that I've got this straight away. So what I need to do now is to say, well, where do those two things intersect? And if you think back to like year 9, what we would do is we'd say, oh, well, the y values have to be equal, right? I do think it helps with this question if you just put your axes in. So we'll do that. Just plonk those into the diagram now. I know this is slow, but the setup in this question is in many ways the hardest bit. There we go. Okay, so we're now looking at this point here, and we're saying this point is where the two lines intersect, and we're going to find all the combinations where that works. So that's why in here I'm working with y and x. I'm not working with any y0, x0, x1, y1. So what we would have done usually is we would have taken this, and we would take this, and we would equate them. And I think if you do that, you're probably still going to get there. But there's a much, much easier way to do it, which is to say we are trying to end up showing that the locus is a circle, and the equation for a circle has x squared and y squared in it. So just take a look at those two equations and think for a minute. Pause the video and have a think about how you can get x squared and y squared in here. And also think about level 3 complex numbers. When you're doing those easy surd equations, how do we always work with surds? And then have a go at finishing this question off, and then hopefully come back and watch the rest of the video. Okay, what I'm going to do here is I'm going to do some rearranging. So tangent 1, we get y minus mx is equal to plus or minus a squared m squared plus b squared. In tangent 2, y plus 1 over mx is equal to the square root of a squared. I've done something wrong here. Sorry guys, I've just realized that m in there should not be m. It should be -1 over m squared. Yep, hopefully no one had paused it and was wondering about that for 10 minutes. Right, so this here is a squared over m squared plus b squared. And now I'm going to square both of those. And I get this for tangent 1. And this for tangent 2. And now we have some algebra to work through. So tangent 1 gives me y squared minus 2mxy plus m squared x squared is equal to a squared m squared plus b squared. And I'm going to write this one out underneath the first one. So I get y squared plus 2 over m xy plus 1 over m squared x squared is equal to a squared over m squared plus b squared. Okay, so now we've got these two equations, and they both need to hold for there to be an intersection. Now, when I looked at this, I really didn't feel happy when I got to this, because I was hoping to see some things cancel out and that I could do some simultaneous equation stuff. But the thing that's kind of getting in the way is the fractions in here with the m in the denominator and the m squared is not nice. So I'm going to clear out those fractions. We'll just write out the first one. We're not going to touch the first equation. This is one of those questions where it feels like you've got quite a long way to go and it's all about to sort of fall apart nicely. I'm going to times both sides through by m squared, and I get m squared y squared plus 2mxy, which should be the moment of great happiness, plus x squared is equal to a squared plus b squared m squared. Now, if you look at that and just think back to like level 1 simultaneous equations, if we add the two things, we get 1 plus m squared y squared. Very happily, when we add these, they go away. And here I get m squared x squared plus x squared, so 1 plus m squared times x squared. Here, the same pattern, I get a squared times m squared plus 1 plus b squared times 1 plus m squared. So we can divide everything through by 1 plus m squared, and we get y squared plus x squared is equal to a squared plus b squared. Right, so now we have really clearly got the equation of a circle, and the center is the origin as expected, and the radius is the square root of a squared plus b squared. So there you go, a really cool conics question. There's another one in this paper that is, I think, a bit harder and has a lot of algebra. I'll try and YouTube that one tomorrow. Please send in any questions that you'd like me to have a go at over the next week. I should get some time to YouTube a bit more later on. Thanks.